let me teach you. Let me teach you what most of you were already ready to do, namely, how do we do the hypothesis test, and what is the hypothesis test that we actually do in this context? There are two of them. Let me see. Yeah, we have to take one on each slide. We want, first of all, and that's the most interesting thing, we want to compare the treatment means with each other. So to be, again, if we want to be technical or formal about that, some would say, if you want to complicate it, then put it into this framework where we say that the null hypothesis is that this individual deviation for each TV set is 0, all of them. No difference at all. The alternative is something is going on somewhere, right? That's loosely said. And like last time, statistical probability theory will help us in that if we measure how different those treatment means really are between each other, that's the numerator of this proportion here, right? That's the sum of squares for treatment. That expresses how different the treatment means are between each other as a variability, right? That's fair enough. That's a variability of treatment means. If I take that relative to the residual variability, it's clear when I have to distinguish signal from noise in looking at means, I should somehow take into account what is the natural level of variability of such data, right? If I want to compare the means, I need to be intelligent about what is the natural variability. Before I can say anything about means really appear different, I need to take into account what the variability level is. So it's a kind of signal to noise. Everything we do in a way in stats is signal to noise comparisons. And that is exactly this sum of squares divided by the right thing, the right degrees of freedom. And here we see that for the first time in two-way ANOVA. Like in one way, the numerator degree of freedom is number of treatment groups minus 1. So that's the same. The denominator degree of freedom, the residual degree of freedom, that's number of blocks minus 1 times number of treatments minus 1. Those two multiplied with each other. The theory tells us that this is then an F distribution under the null hypothesis, assuming the null hypothesis that the means are really equal. So that's the usual reasoning of hypothesis testing. Assuming the null, we look at some statistic that measure what we're interested in, namely mean differences. This is a measure of mean differences. If all the means are exactly the same, the numerator would be 0, right? Each individual contribution would be 0, 0, 0 because they're all on the mean. So a 0 here, that's a 0 signal, so nothing is going on. On average, such a signal would not be 0 because we have natural variability. So on average, actually, this one would be 1. If nothing is going on, if we have a larger signal here, if the means are really more different than we expect, then we call them significantly different, right? So if they're very different, we call them significantly different. This is just to make the distinction between where is the limit between noise and real signal, right? That's what it's all about. We can actually do that for the blocks also, as I've said a couple of times already, and the slide is exactly the same slide, apart from the numerator. Now it's number of blocks minus 1, not number of treatments minus 1. Otherwise, it's exactly the same issue. And then we could look at the F again. I'm going to skip that, actually. We looked at the F distribution last time. Instead, let us look at this summary of everything. Almost the same as last week. The only new thing is this, that we have a row in the output. We saw it already from R. That summarizes block differences. We have a row to tell the story about treatment differences, one row to tell the story about block differences, one row to tell the story about residual variability, and then in R the bottom total row is not even there, as you can see. So here is the output in R that matches the formal table. All the formulas are there. What we in a way compute is the sum of squares. That's where, if we were to do this by hand, we're not, but if we were, that would be where we would start. Then we would take care of knowing what the degrees of freedom are. Having all those sums of squares, I could just divide by degrees of freedom, and then I get what people would call not the sum of squares, but the mean squares, assuming that we divided by the right thing, the right degrees of freedom, which is number of groups minus 1, number of blocks minus 1, and then the multiplication of these two numbers in those three cases. The F statistic is basically this mean square divided by this mean square, and this mean square divided by the same MSE. That's the F statistic, and then we look up in the right F distribution to check what are the p-values. So we could do that with PF ourselves if we wanted. And in this case, what are the conclusion on the treatment means? Are the treatment means different? You're not tested now? You're not counted? Yes, they are. Good. I hope you'll not. Yeah, okay. What about the block means? Are they different? Yes. Using the usual 5% limit. I would be less, more. But yeah, it's below 5%. So if we are forced to a yes-no way through the world, the answer would be, are they different? Yes, they are. Question? Blocks are persons shown to be different, you say? So then the question is, what then about this analysis of the products when the blocks or the persons are really different? Well, good news is it's okay. That's the whole idea of it. It's okay what we do when persons and blocks are allowed to be different. That's the nice thing about this approach, that they are allowed to be different. We even expect them to be different in a way, because that's why we did such a design in the first place. That's because we, in a way, expected that to happen. And in the analysis we do, we take it into account in the right way. Let's go back to that. It's a good question, actually, get me the chance to emphasize that. The good news is that when I take the mean square for treatment and I divide by the mean square for residual to test the significance, in a way take the signal dividing by the noise. This noise measure here, the residual noise measure, has been cleaned out of potential block and person differences. It's not part of that noise measure. So it's part of the whole idea of this way of doing such a study in the first place, and the following computations due to the very, if I am running far, but due to, in a way, this one, saying that I'm actually taking this potential block and person difference out of the equation explicitly, directly. It's being taken out in a way. And it's allowed to be there, because I just remove it if it's there. If it's not there, I don't care. But I'm using residual variability, and it's not coming from persons being different. So it's okay. Persons, that's what you're saying in clinical trials. You say persons become their own control. Right? You have a person, you get the different treatments. So it doesn't really matter whether you're a high reacting person. It's not part of the computation for saying something about whether the treatment works or not. Whether you're a high reacting person or a sort of a low reacting person, it doesn't change anything, because you compare all the products on you. So you compare you with this, you with that, and you with that. So whether you are up here all the time, it doesn't matter. because it's being corrected for in the model. We correct for those differences, and it's the whole purpose. So thanks for making me emphasize the whole purpose of this thing, actually. You were mentioning scales. That's a whole different story. Scales is a complicated issue sometimes. The question is this sharpness scale, what about this? Well, there could be scale issues, which we assume we don't have any problems with for such an analysis. I mean, how to scale things and how, whether it's really quantitative and anything, that's a whole different story. Exactly. Now you say, I've been working with that for 25 years. She says that people can use the scale differently. Yeah, but they're allowed to. Hey, it's a free country. And they're not fired by Bang & Olufsen nor by any other food company when they do those, because people do use the scale differently. And that's what we correct for. At least the basic way of using a scale differently, because there is a more extended, challenging way that they could be different, which we do not discuss for now. But I did a lot of research on that, so if you get the problem, come to me. Anyway, thanks for the very good question. Let's do one more, and then we do a break. Pick another true statement. That's difficult. I'm pushing you a little bit here because, I mean, I use some, for some of us, standard terminology that you didn't really have the chance to practice a lot. So it's fair enough. And also the root sign there is not so visible. The residual standard deviation is the square root of the residual variance, just to start there, right? Residual variance, the SSE, or rather, it's the MSE, mean squared error, that estimates the residual variance. The sigma of the model, actually, I didn't put that on a slide, but we talked about it a little bit last time. And the sigma in the model assumption is actually estimated by 2.696, the MSE, the mean squared for errors, the residual MS, which makes the blue answer the correct, because then I take the root to get the residual standard deviation. So that was just a bit of terminology that we could get used to here. Expert is doing as an expert. So let's break it 15 minutes, 1 minute, 2 minutes after I begin again.